Hello and welcome to GeoProven and Part 3 on our lecture series on transformations, mathematical techniques that have wide application, including crystallography and computer graphics. In the previous two videos we looked at the translation transformations, and then the last video, Part 2, we looked at rotational transformations. In this video, Part 3, we're going to be looking at reflections. We're going to be looking at three different reflections. The first one is over the x-axis. And we've been playing with a slice of deep dish Chicago-style pan pizza. We translated it originally in the first video from a position more centered up to where we put the corner at the origin. So we can look at the figure as it reflects over each of the axes, the first one being the x-axis. We've been working with a random point or an arbitrary point, 7, 4. It plots there in the middle of the sausage on the edge of the pizza slice. With reflection over the x-axis, you can think of every point going over the x-axis at 90 degrees and going a distance equal to how far away it is from the axis. So it goes to the axis and then beyond an equal distance. So the arbitrary point 7, 4 goes from a point above the x-axis along a 90-degree transect across the x-axis to a point below the axis. The vector notation for reflection over the x-axis is an R with a subscript x-axis or x-axis. There's a coordinate rule, which is a little bit more informative. Takes any point xy and maps it to or goes to the point x minus y. Looking at our arbitrary point then in the middle of the sausage, it goes from the point 7, 4 to the point 7 minus 4. They share the same x distance from the y-axis along the x-axis. X distance is 7, but the y distance went from 4 above the x-axis to minus 4 below. So if we do that for all of the points in the figure, reflecting them over the x-axis, this is the reflection point, or reflection figure down in the quadrant 4. It kind of looks like Pac-Man. Wugga 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 wugga. Maybe you have to be a little bit older to remember Pac-Man, I don't know. Pretty iconic, pretty famous. I think probably everybody's seen it. Anyway, after the reflection over the x-axis, this is what the final figure looks like when you get rid of the ghost image. So looking at a reflection now over the y-axis, the second variety. Here's the pizza slice, again with the corner at the origin. This time we're going to go over the y-axis. Here's the arbitrary point 7, 4. It's going to go over the y-axis. Similarly, as if it were going over the x, it's going to go the same distance across y that it took to get to the axis. So there's the point going straight across the y-axis at a 90-degree angle. The notation for that is an R with the subscript y-axis. The coordinate rule for that transformation is to take any xy and map it to the point minus xy. So for the arbitrary point shown, it goes from point 7, 4 to the point minus 7, 4. So it goes, the y is shared, the y is the same value, 4. The x value went from positive 7 to minus 7, the same distance away from the y-axis. If we do that now for every point in the pizza, this is what we get. So every point is moved across the y-axis an equal amount. If you get rid of the ghost image, you're left with the final position of the figure. So the last reflection that we're going to look at is over the line y equals x. So we start with the original figure with the corner at the origin, piece of slice. And there's the random point in the sausage, the arbitrary 0.74. And there's the line y equals x. It's got a slope of 1. Now the point is going to go across that reflection plane, or reflection line. Think of it as a mirror. The point is going to go 90 degrees across the line, just like it went 90 degrees when it went across each axis. The vector notation for the reflection over the line y equals x is with y equals x as a subscript in the letter r. The coordinate rule notation for the reflection over the line y equals x is that the point xy goes to the point yx. So the coordinate indices are swapped. So the example point goes from 0.74 to 47. If we look at the line, the red line goes from the old 0.74 to the new 0.47. We can calculate the slope of that line as the rise over the run. So that would be the change in y, the difference between 7 and 4, the new point to the old point, over the run, the difference in x, from the new point 4 to the old point minus 7. When you do that, you see that the slope of the line is minus 1, which is the reciprocal opposite of the slope 1, the slope of the line. Which, if you think about the slope of y equals x being 1, minus 1 is a reciprocal opposite slope. So those two lines, the red line and the line y equals x, are at right angles to each other. So each and every point is going to move the distance that it takes in a 90-degree sense to get to that mirror plane, the line y equals x, and then over onto the other side. Some of the points go over the line in the other direction. So if you look at the orange sausage and the magenta sausage, it's going to go down below the line y equals x. Meanwhile, the gray sausage, along with the arbitrary 0.74, and the brown sausage are going to go above the line y equals x. So you get a little bit of a mess, but if you remove the ghost, you can see the reflected image. So here then is a summary of the transformations. We've now completed the reflection transformations, so that completes our list of the isometric transformations of translation. We gave one example of that, and that was actually moving the pizza so that its corner was on the origin. We then, in video 2, we looked at 3 different rotations, and in this video we just completed 3 different reflections. Those are all of the coordinate rules that are involved in each one of those separate transformations, as well as an example of the arbitrary 0.74 and how it's manipulated into its image point from its pre-image point. I hope you enjoyed that series. The next, now that we've covered all of the transformations, the isometric transformations in the video series, the next part, part 4, is going to be on composite transformations. What happens when you do several successive transformations in a row? So please join us for part 4.